Right. So trying to understand what is light color. First of all, we know that waves can have different frequencies like this and different amplitudes. If we have a different amplitude, a light wave would have a different brightness. So if it's high amplitude, it would be bright. If it's low amplitude, it would be dim. The color is actually down to its frequency. So if there's a different wavelength or different frequency, we see a different color. As long as it's within our range of seeing, because remember that light is just an electromagnetic wave. So in other words, it's part of the spectrum, the electromagnetic spectrum, which is just essentially a family of all different types of electromagnetic waves. There's nothing to determine one electromagnetic wave from another. It's just the fact that one has a different frequency than the other. So all the way over here, we have waves, electromagnetic waves of 100 million meters, which we would call, and then all the way down to 100 meters. Anything between around this range we call radio waves. Between this range we call microwaves. Over here we call infrared, and then over here at the other end we have gamma rays and then X-rays and ultraviolet. But this tiny little sliver in between, which isn't even to scale, it's not even as thick as it makes out there. It's almost unnoticeable on this diagram if you drew it to scale. It goes from 400 to 700 nanometers. So if you studied how these are increasing and decreasing for a moment, you'll notice just how tiny a fraction of the electromagnetic spectrum that we can actually see. We can hardly see anything. But it doesn't seem that way because that's the only thing that that's just what we were used to. We've seen what we always see. But within that tiny sliver, the smaller wavelengths our brain sees as sort of blue or violet, and the larger wavelengths our brain sees as red. Now, the reason for that is because of how our eyes work. Our eyes detect electromagnetic waves, but only of that of that range. And the way it does it is by using cells at the back of our retina called cones and rods. Now, rods detect everything, all the colors, and they don't have any preference really, as long as it's within that range. And so they're a lot more sensitive. They can detect light in when it's quite dark. Cones, however, aren't as sensitive as rods, but they are sensitive to specific wavelengths or specific colors of light. So we have a green, red, and a blue cone. So if we go over to here, we can see their sensitivity. So basically, and we got these are the wavelengths here. We've got 400 to 700 nanometers, just like the picture just above here. And our blue rod is particularly sensitive at 445 nanometers. Our green rod is particularly sensitive at what looks like 555 potentially, and our red rod is particularly sensitive at 575. So if I were to shine blue light at my eyes, my cone rods would see a lot of activity. It would detect quite a lot of radiation, quite a lot of electromagnetic radiation. Whereas my green cones would detect a little bit, but not as much. My red cones wouldn't detect anything. And this is the information that goes to my brain, and then I use that to make sense of the world. Then, likewise with my violet lights, now I'm all the way over here, not really seeing any activity from my green cones, and none from my red. And so again, my brain decides we're going to call that very blue. Okay, that's how we'll define that. And so the same with my red light, dark red, and so on. If we look at yellow, with yellow, we actually get an equal amount. We have our blue cones won't detect anything. Here's our yellow light here. So our blue cones don't really detect anything. But our red and green cones detect roughly the same amount. The same with cyan, which is a kind of sort of sky blue color over here. And the cyan detected our blue cones detect a fair amount, and so do our green cones, roughly about the same amount again. So basically, computer monitors and TVs take advantage of this rather than buying, thousands and thousands of different LEDs of all the different wave producing all the different colors, all the different wavelengths of light. They just get 3. They get one for blue, one for green, one for red, and then they just mix them together to get to simulate the other colors. So because when I saw yellow light, then my green cones and my red cones fired, then I could just shine green and red light at my eyes, and I would see just the same thing. So this yellow rectangle here, because it's coming from a computer monitor, there is no actual yellow light coming from there. Your eyes are not seeing a single photon, a single wave of yellow light at that point. Although your brain has no idea, because all it knows is that my green cones are firing and my red cones are firing, just the same as if you were seeing yellow light. There's no difference as far as your brain is concerned. You don't detect yellow light directly. You simply detect your green cones and your red cones are both firing when you see yellow light, and they're also both firing when you're seeing green and red light. So it's the same as far as your brain is concerned. So if you look closely at a computer monitor, it would look like this. And so basically just red, green, and blue LEDs, and then mixed together a different amount to show different colors and pictures. So let's have a look at animation of how this would work. Just pause. So let's have a look at a regular light then. So we're shining yellow light. This is, as far as the animation is concerned, this is yellow light. And if I shine green light, red light, this is red, as far as he's concerned or she's concerned, and it's the same. It is actually red light, okay? Same as all that. Now, if we come out and we just, instead of using the different actual colors, we mix them all together. If I shine red light, it sees red, but if I shine red and green, they see yellow. There's no yellow light going into his eyes, but if there were, he would have, or she would have, exactly the same experience. And if we can do this, we can do the same thing with green and blue. We would see cyan, because if it was cyan light, it would be the green and the blue cones would be firing as well. So a lot of people say that magenta doesn't exist or pink doesn't exist, and that's because when you shine red and blue, we end up seeing magenta or pink. But if there's no way that could happen in real life, because essentially it would be the brain could imagine it would be somewhere between red and blue, but that would be green, and your green cone's not detecting anything, and so it just makes a color up. That's the story. I think that's since been proven not the case, but I'm not sure about that one. I can't remember. I haven't looked into it, but now if we bring in green now, we now see white. So white light is a mixture of all the colors, okay? And you can obviously change the intensity of some of these to get different colors. You mix them all together and you can get a variety of different colors. And that's essentially what what your TV is doing or your computer monitor is doing, okay? So that's color and wavelength.